We talked yesterday that standard state implies what? Standard.
25 degrees.
25 degrees.
25 degrees C, 1 ATM, and 1 molar concentration. And I told you in the Nernst equation that we will not be changing the temperature and we will not be changing the pressure. The only thing we are changing to go from standard conditions to other conditions is the concentration. Therefore, we can simplify this equation by doing some math. These then are constants, right? T becomes a constant. And so we're pretty much good there. When we take that, multiply the 8.31 times 298, divide it by Faraday's constant, and we get a number. Then we multiply that number by that E value that we've been talking about, and it takes it from the natural log to the log base 10, which simplifies the Nernst equation to this. Happy? Because this involves a lot less math. All right, now we stopped our fun parade yesterday right at thermodynamics and electrochemistry. It's thermodynamics, comma, electrochemistry, and equilibrium. I'm going to now marry these all together because you need to. Thermodynamics, the overriding principle in thermodynamics is Gibbs free energy, delta G, and delta G tells us what?
Spontaneity.
Yeah, the spontaneity. And that is telling us whether something will occur with outside intervention. And for equilibrium, we talked for a good 6 weeks about the constant K. All right, and K tells us in our reaction, all of which are reversible, on which are favored, the reactants or the products, right? So we now know how K fits into any reaction. Now we're going to talk about electrochemistry, and we talk about the E cell potential, and specifically in a redox reaction. And a positive value tells us that it is a spontaneous, and a negative value tells us that it is non-spontaneous. Okay. So now we're going to put these all together in this really nice triangle of knowledge. We learned just yesterday that you can relate Gibbs free energy to the cell potential by using the amount of energy available to do work is equal to negative none-V. We knew, and perhaps we skimmed over this, that delta G and equilibrium are tied by the formula delta G equals negative Ratlink. Now K and the E cell are related via the Nernst equation, and let's make this an easy thing. The log K is equal to, I have to even turn and look at this so I don't write it backwards. Log K is equal to the number of moles times the E cell over 0.0592. These are equivalent terms, right?
Why is it log K instead of natural
Okay.
log?
All I did was rearrange, remember, just like I showed you when I changed the Nernst equation?
It's at the top of your
All I did was change it around a little bit. This is an easier form. This is what appears on your green sheet, and I would prefer that you use in practice what you're going to see on the AP exam. It's the same thing. I've just rearranged terms. Okay, are we good? Now, let's recall the way the universe likes things to work. The universe is happy when delta G is less than 0, when K is greater than 1, Remember that as K is less than 1, that favors the reactants. When K is greater than 1, that favors the products. And when a cell is spontaneous. Right. Any of these conditions not being true would be an impediment to the reaction occurring. Everybody good there? See, you zombied out already.
Wait, so K, so it's favored when K is greater than 1, so when it favors the product, you said? I thought you wanted more reactants, but that means it's a longer lasting battery.
Okay, we're not talking about a battery, we're just talking about
Universal
life in
lifespan.
general.
Oh, okay, because I saw the delta G, and the E cell was greater than 0, which means a good battery. So, okay.
Alrighty. So I envision somebody coming up to you on the street and saying, hey, see this reaction right here? Could you please tell me what K is for it? I just want to know. And you would say,
Sure.
all right, I can do that, I can do that. And what you would do first is write the overall reaction. And then with your standard reduction potentials, you would figure out which one was reduced, which one was oxidized, find the E cell. I've already done that. I decided that zinc was going to be oxidized, so I flipped it around, changed the sign, and I got an E cell potential of positive 1.56 volts. Now I want to solve for K. The log of K would then be equal to the number of moles of electrons, 2 times the cell potential, 1.56 volts, over that magic number. Can you do this on your own?
Yeah, I think it's around 10 to the 52.8.
Yeah, I think it works out right here. The log of K is equal to 52.88. Okay, I need to know K, not the log of K. So K is equal to 10 raised to the 52.88, which is a number that you're going to do in your calculator.
1.32.
Got a lot of this.
Oh wait,
I mean, if
not
I want
negative
zero.
52.
Not negative.
Five.
Not negative, yes.
5.0 times 10 to the 52.
Okay. 5 times 10 to the 52nd. All right, now, tell me what you know about this.
That's not what I got.
That's not what I
K's
got.
are usually the
So
negative.
That's what I got.
Well, I got
It just made it
52.7.
You know what? I don't really care what the coefficient is. Times 10 to the 52nd pretty much trumps it all.
Yeah.
So times 10 to the 52nd is correct. What does that say?
It means it's a
Really small.
far shifted.
Yeah, this is going to completion. Everything is favoring this reaction going in the forward direction, yeah? Would this make a good battery?
Very good.
Yeah, it would. Make a great battery.
If
It's going this way.
I thought if it went to completion faster, that would mean it would die faster.
It doesn't mean it would go to completion. Would it go to completion faster? No. Would it go to completion? Yes.
It's
What
definitely
goes
head that way.
faster, what determines is the number of moles of electrons. Okay? So if you had that manganese going from plus 7 to plus 2, that would be 5 moles of electrons, and then it would be going quicker.
So wouldn't it make it, so it would really make a big difference if the E's were way different, so that the E value would be huge, and then it would make the
Yeah,
exponent large?
yeah. So
like
remember,
if you had
on some equations, we have the lowest common factor is 10. So that means that one of those is going 5 times for every 2 times the other one is going.
Yeah,
Yeah.
okay.
Okay. So now I suspect that you can do this on your own, and I will ask you to do that in a minute. I'm not going to, okay, put that aside. I want to continue to film so I can do it in one shot, so I'm not driving myself crazy. You need this, and you need your pink sheet or your white sheet.
But
Okay, One of the questions that you will be asked quite often is, who is being, in a chemical equation, what is being reduced and what's being oxidized? That's not hard to tell when you're looking at the whole balanced equation. The same question could be asked by you just looking at values, standard reduction potential values. Okay, so let's say I have lead plus 2 and bromine. These are both standard reduction potentials. Of these two species, which one will be reduced and which one will be oxidized? Okay, bromine is going to be reduced. Why? It's higher on the list. It has a more positive standard reduction potential than the lead does. Everybody's good with that, right? Okay, now, when we write this equation out, these two guys, one of them has to be changed to an oxidation. So we're going to have the bromine staying as a reduction potential, and we're going to have the lead will be changed around. Oh, look. Kind of just like left that go, didn't I there? All right, 2 bromines. And this will go to lead plus 2 electrons. Are we on the same page there? Okay. Now, this you said was the reduction, and this is the oxidation, yes?
Yes.
This bromine is the species that is reduced, and it acts as the oxidizing agent for the lead. Yes? Okay. The lead is the reduction agent, reducing agent. So the bromine is forcing the lead to give up its electrons. We see that as well, don't we? All right. Now, it is not unheard of for these questions to take this form. Okay, let's say I have lead plus 3 and this and okay. Which one will be reduced first?
Chlorine.
Okay, then which one will be reduced?
Iron.
And then which one will be reduced? Magnesium. Yep, that is true. Okay, did you see how we did that? All we did was rank them in terms of their standard reduction potential. So 2.87 and what's the iron? 0.77, and then magnesium was way down here somewhere.
Negative 2.37.
Thank you, negative 2.37. Okay.
How does battery look?
It isn't a battery. Remember, not everything is a battery. It just is right this moment in time for us. We haven't learned anything different. Okay, now, that was a pretty easy question. Now tell me, what serves as the oxidizing agent for fluorine?
Iron.
Huh. Well, that's a little more difficult, isn't it? So if I'm saying here, this is the reduction, correct? And it's acting on the oxidizing as the oxidizing agent. Given these three things in a beaker, what is going to be oxidized?
The other two.
Yeah, but yeah, the other two. In what order?
Oh.
Magnesium, no,
It's
iron.
iron than
Iron and then magnesium, in my opinion.
So you can add,
Mhm.
so you can subtract 0.77 and then add
Okay. So because you told me it goes in this order, 1, 2, 3, yep. So if this is reduced, then this is oxidized, and then it is reduced next, and then this is oxidized, and then this is reduced. Yeah? So how do you figure that out? This way. Okay. The diagonal rule of reduction, write the most positive half-cell reaction on top, list the subsequent reactions according to their standard cell potential. The reactant on the uppermost will be reduced and act as the oxidizing agent for the product. Get how that works?
Yeah.
Okay, so look at here. I have done another example, and I've listed them in order of
Easy.
E cell potential. So this would be reduced first, second, and third. Chlorine acts as the oxidizing agent for bromine, the bromine ion. This acts as the oxidizing agent for this. Good? Okay. That's pretty much all I want to say today. I want you to do that practice problem.